Greetings. So, we are going to discuss the no-clone theorem today. We will also talk about a few other things in quantum information science and quantum computing. But the essential point to know, even as we begin a discussion on the no-clone theorem, is to recognize that cloning in physics is exact. It's not how it is in biology, okay? Or we use the term cloning, copying, okay? But the terminology, you have to be careful with it because it has a much more precise meaning than what it has in some other context. So, it is called cloning, and we will be talking about cloning and copying, but it is far more exact than how it is in other situations. So, what is cloning? What is to copy? So, suppose you have got a photocopying machine and you put a picture of the Taj Mahal, and you put the picture of the Taj Mahal, then you also insert a blank sheet of paper, otherwise you get nothing, right? So, there is some ancillary material which is the blank paper which should go in, and that is the one on which the copy will be made. So, you need some material, and what comes out of it are two copies, right? This is cloning, this is copying, this is what we mean by copying. And the copying machine would be useless if it can copy only the picture of the Taj Mahal, right? It has to be able to, it's a copying machine, it has to copy whatever you give, right? So, if you give the Qutub Minar, you will get two copies of the Qutub Minar, okay? Or you can give a copy, to copy you can give a picture of the Taj Mahal with the Qutub Minar, and you expect it to produce two copies of that. So, in every situation we are going to be confronted with, when you talk about copying, then you really want to talk about copying a natural system, what exists in nature. And nature is not classical, okay? Copying is some sort of a simulation, right? You are producing a copy which simulates the original, and if you are trying to simulate nature, then what you need is a copier which is not just the classical copier, but a quantum copier. Okay, it has to be able to copy quantum objects. And the question is, this being the situation, can you do that? And what is different in quantum nature and classical nature, which is really only an approximation to quantum nature? It is not that nature is divided between the classical world and the quantum world. Nature is quantum. Everything in nature is described correctly only by quantum theory, whether it is the behavior of an electron in an atom or the motion of galaxies and big objects. So, one should not have the notion that quantum theory applies to small objects and classical mechanics to large objects. When quantum theory is introduced, whether the principle of uncertainty or the Schrodinger equation or whatever, do we ever say that, okay, up to this mass or up to this size the law works? Never. Okay, that's just the law of nature as it is. And nature is described correctly by quantum theory it is described usefully by classical theory. It may be immensely useful, sometimes even more useful than quantum theory if you are describing, how cars are moving in traffic. It may be more useful to describe it using classical theories, but it does not mean that that description is exact. And if you needed a more accurate description, that would be available only if you used quantum theory. That is the reason Feynman says that nature is not classical. It is not that there is a part of nature which is quantum and another which is classical. Whole of nature is described best only by quantum laws. And if you are now trying to simulate nature, you are making some sort of a copying machine, okay, a cloning machine, then you are going to look for a cloning machine which will follow the laws of whose operation is correctly described by quantum laws. So, that is what we are going to look for, and this is an important part of simulating nature and an important step that you need to recognize in your discussion on quantum information science, quantum computing and so on, because that is what you are really confronted with. So, this is what a cloning machine is. You put in an object, no matter what it is, whether it is the Taj Mahal or a picture of the tiger or an elephant or whatever, and you are using the cloning machine to get two such pieces. And whatever you do, the input consists of the object to be cloned, the ancillary material that you are going to use from which the clone would be made, okay, and the machine will give you as output the original and a ditto copy of the original. That is what you are looking for that is what you expect from a cloning machine. So, now system is described by a state vector in the Hilbert space. Okay. So, there is a physical state which is a certain state to be copied. It will be copied on an ancillary known state, okay, and you will get the original state from this quantum copier and a copy of the same, which is made from the ancillary material. So, this is the model that we are discussing now. Now, it turns out that such a quantum copier does not exist, and it not only does not exist, it cannot exist. And this is known as the no-clone theorem of quantum information science, okay, or the no-clone theorem of quantum computing, because when you are processing qubits, okay, will you be able to put it through some gates which will generate a quantum copying machine which will give you an exact copy of the original qubit. So, that is a question that you often have to deal with, and such a quantum copier does not and cannot exist, which is a negative result, but a very important one in quantum computing and quantum information science. So, this is this theorem is due to Wouter, Zurek and Dix in 1982, around the same time that the Deutsch algorithm came up, and that is around the time that Feynman made his brilliant suggestion, right. And of course, exact copying is not possible because you need every single property of the original object to be duplicated, and every possible property of the original cannot even be determined, because some of those properties are not compatible. Measurements on some of those quantities are not even compatible. If what you want to duplicate involves information about the position and momentum of something, you know already that this information is not accessible. Okay? So, the uncertainty principle is going to limit the information which is available to you. But the theorem is a very rigorous theorem, and let us see how it is proved. So, we agreed that the cloning machine has to be able to clone whatever is input to it, whether it is the Taj Mahal or the Qutub Minar or whatever. Likewise, the quantum cloning machine should be able to clone any state vector that you feed into it, which describes the physical state of a system. So, that is your expectation from a cloning machine. That is what you will call as a quantum cloning device. So, it should be able to clone if you put in the vector A or the vector B, and the vector A in general is not in a pure state, nor is the vector B in a pure state. Both are in a superposition state, right, because you cannot factorize nature between slit 1 and slit 2 in the Young's double slit experiment, or between a cat which is dead or alive, or between a switch being on and off, right. Physical nature requires you to describe this in terms of superposition of the alternative states, or what we classically called as alternative states. When we describe them correctly, we have to consider the probability amplitudes of both the states, and then we have to reconcile with the interference that this generates. So, whenever the two paths are available to a quantum system, all right, you are led to interference. If you close one of the paths, then you destroy the interference, right. If you do anything to mark which path, so this is the which way path experiment in the Young's double slit language, but it is applicable to every quantum phenomenon. If you do any marking, then you lose the interference, and if the marking is erased by a quantum eraser, then you recover the interference. Okay? So, that is the quantum world that we live in. And we will now consider cloning, or an attempted cloning, if we might wish, of two vectors, each being in a state of superposition of 0 and 1. So, this is a single qubit, okay? And alternatively, the other vector, which is also a superposition of 0 and 1, but then it is a different superposition, the coefficients are different. Okay? So, one has the coefficients alpha 0 and alpha 1, the other has beta 0 and beta 1, both are normalized, and we can take care of all that, all right. So, this is the superposition state that we will talk about and attempt to clone this, and I am careful about using the term attempt to clone and not clone it, because such cloning is not possible. Okay? This is the no clone theorem. So, what does the cloning operator do? So, we will now represent the cloning machine by an operator omega with a subscript c, which will achieve the cloning, which would achieve cloning. So, you feed in a single qubit into the cloning machine, represented this process of cloning by an operator omega, which will operate on the operand, which is the input state vector. But the input state vector by itself, you know from the very beginning, also needs an ancillary state vector. So, the input is going to be the direct product of what is to be cloned and an ancillary vector. okay, and the cloning operator will operate on that and give you the original vector and a copy of the same. So, these are the two qubits that we will attempt to clone. Both are in a state of superposition, right. What has the cloning operator done? It operates on the input. The input is the direct product or the tensor product of the state vector, which is the ancillary vector, and the vector to be copied. Okay. The cloning operator will operate on this, and we are looking for an operator whose result will be the right hand side, which is the tensor product of the two output states. Okay, this is what we are looking for, and we hope to achieve this for the state vector psi, which is a 1 qubit state, or a different 1 qubit state, which is phi. Okay. So, this is if it operates on the direct product of phi and the ancillary vector psi a, then it would give you two copies of phi. So, which is the tensor product of phi with phi, or the direct product of phi with phi, or you may get the direct product of psi with psi if the input is psi. So, this is good. This is what you expect the cloning machine or the cloning operator to achieve. So, we will also discuss, because we know we have sufficient experience with quantum theory by now, and we know that it follows rules of linear algebra, linear vector space, right. And therefore, the cloning machine should be able to do this also for this, for even if you mix psi and phi. If you add up the two, the cloning operator should be able to give you the corresponding result. So, this is the result that you expect from a cloning machine. The cloning operator operates on the direct product psi with the ancillary vector, gives you two copies of psi. When it operates on phi with the same ancillary vector, you get two copies of phi. And now, if you mix psi and phi, you construct an admixture of psi and phi. Then what does your linear algebra of quantum mechanics tell you? It should be able to give you a copy of this superposition, right. So, this is the question that we are going to ask now. What will the copying operator give you if the input is a linear superposition of one qubit psi and another qubit phi? That is a question. And we now need to answer this, but we can answer it using two alternative ways. One, using the linearity, the linear algebra properties of quantum mechanics that we are familiar with, and we will also answer it from what we expect the cloning operator to do, having defined the cloning operator already. Okay? So, we can use these two alternative ways of doing it. So, the linearity property of quantum mechanics tells you that if you operate on this superposition alpha psi plus beta phi by the cloning operator omega, then you should get alpha times omega operating on psi product psi ancillary vector plus beta times omega operating on phi times the ancillary vector, right. And what does the omega operator do? It will give you two copies of psi from the first term and two copies of phi from the second term. So, this is what you expect from the cloning mechanism, okay, from the linearity of the cloning mechanism. Okay. So, we have used the linear property of how operators operate on an operand. So, if the operand consists of a linear superposition of two vectors with appropriate coefficients, then you get the result is the sum that you will get from operating by the operator on each of the component scaled by the corresponding coefficient and then sum up the results, right. So, that is the usual property of quantum theory that we have used. So, essentially this step has heavily used linearity. Of course, it has used the cloning feature. But now from the cloning feature alone, what do we get? From the cloning mechanism, you are doing the same operation now. Okay? It is this, that you are trying to clone a superposition of alpha psi with beta phi. So, this is what you are trying to clone. So, you must get two copies of the superposition. So, we have answered this question using two alternative mechanisms, alright. Both are common standard practices in quantum theory. There is nothing new that we have added to our quantum algebra, right. Essentially the well known rules of quantum mechanics we have used, and we must ask if the result that we get from these two alternative ways, are they equal? They better be, if this logic is sustainable. Okay? So, we are going to ask if what is in the upper rectangular box is equal to what is in the lower rectangular box. Are the two results exactly the same? So, let us ask this question. If the left hand side is equal to the right hand side, so the same two terms I have written here at the top, okay, of the slide. And now you can spell out what these terms are, and you recognize that on the left hand side you have got alpha times 2 copies of psi and then beta times 2 copies of phi. That is what you have on the left hand side. What do you have on the right hand side? You have got 2 copies of the superposed states. So, this is the question that we are asking. Are 2 copies of the superposed state given by this sum, which is alpha times 2 copies of psi and beta times 2 copies of phi. So, are these two exactly equal? So, let us expand the right hand side using your usual laws of quantum mechanics. So, you are constructing the tensor product of alpha psi plus beta phi with alpha psi plus beta phi. So, do it term by term. So, from the first term here and the first term here, you get alpha square psi times psi. From the first term here and the second term here, you get alpha beta times the tensor product of psi with phi. Then you get beta times alpha, phi times psi, and then beta square times phi times phi. So, those are the 4 terms that you get. And under what condition will these 4 terms be equal to what you have on the left hand side? Okay, if the logic is sustainable, then the left hand side better be equal to the right hand side. So, we immediately recognize that equality is possible if and only if alpha square is equal to alpha, because the coefficients of the corresponding terms must be equal, right. Beta square must be equal to beta, and alpha beta, which is of course the same as beta alpha, should be equal to 0. Okay. And that is going to be possible at least if alpha is 0 or beta is 0 or both are 0. And if either alpha or beta is 0, the superposition is destroyed. Okay, there is no superposition to talk about, because the superposition is made of alpha psi plus beta phi. Okay, which means that a qubit cannot be cloned. Okay? So, this is the no cloning theorem, and we have seen that the proof is based on very simple considerations in quantum mechanics, and a qubit simply cannot be cloned. So, a quantum copier does not exist. Not only does it not exist, it cannot exist. So, this is a very important theorem by Wouter, Zurek and Dijks, and now quantum computing has advanced to a great extent. You are going to be talking about multi-qubit entanglement. We talked about superpositions of 0 and 1, which gave you the single qubits. We also discussed the 2 qubit systems, right? And then of course, to really get full advantage from quantum computing, you need entanglement of multi-qubits, and this IBM quantum computer that you can log into uses 2 processors which are 5 qubit processors and 1 processor which is a 16 qubit processor. Google has claimed that it has a 54 qubit processor, and I am not going to discuss the debate whether this claim has been validated or not. Okay, that's a big debate, and I am not going to discuss that. But a 54 qubit processor that Google has claimed would be a huge thing. Okay, means if you just it will have 2 to the power 52 states it can handle simultaneously. So, that is a huge number, all right. Means the number of atoms in the universe is estimated to be somewhere between 2 to the power 264 and 2 to the power 272, that is the rough estimate. So, as the more qubits that you entangle, you succeed in entangling, your capacity to process information, which is essentially of quantum nature, is going to be enormously huge. And this will have a major impact on technology, because you can now make quantum gates. You have already used the control NOT gate and some of the gates which are the single qubit gates and also the 2 qubit gates, and using these gates you build quantum circuits, and using these quantum circuits you can build quantum computers. So, the single qubit state has got 2 complex numbers, but then you really need 2 less than that to describe it, because of what we have discussed at great length earlier, and you really need 2 real numbers to describe a 1 qubit state. If you have a 2 qubit state, you need again 2 less than 2 to the power n plus 1. So, you need only 6, okay. And for 3 qubits, you need 2 to the power 3 plus 1 minus 2, which is 2 to the power 3 minus 2. So, you need 6 states over here, right? Yeah, 4 minus 2, yeah, yeah. And then if you have n qubit states, then the number of real numbers will be 2 to the power n plus 1 minus 2, okay, yeah. So, let us consider a 3 qubit system. So, 3 qubit system will have 2 to the power 3 states, right, and you can write it as a triple sum over I, j and k, which you can use as dummy indices, which run over all the values they can take, and they can take 2 values 0 and 1. If k takes 2 values 0 and 1, then you get 2 terms on the right, but then you are left with sum over I and j. The sum over k is already carried out. Now you can carry out the sum over j, 2 terms for each of value of k. So now you have these terms, and then finally you can let I take 2 values, and you have, these are the 8 possible states that you have, whose superposition will give you a 3 qubit state. It may or may not be entangled, and we know how to describe entanglement. If it can be described as a product of lower qubits, then it is not entangled. It may also be partially entangled or not at all entangled. Okay? So, you have these 8 terms with, there are 8 coefficients, and all of these coefficients are such that the probability of measuring of finding that 3 qubit system to be in the state ijk is given by the modulus square of the coefficient alpha ijk, and if you sum over all of these coefficients over I, j and k, then the unitary transformations guarantee that the norm will be preserved. So, if you go to a higher number of qubits, you really have a huge amount of information that you can process. As the n increases from 1 to 2 to 3, you have seen how rapidly it grows, right? The amount of information that you can process shoots up exponentially, and that gives you a power which ultimately beats the power of using many classical computers even in parallel. Okay, classical computers, of course, you can augment the power by putting them in circuits such that their processors process parts of the problem in parallel. Okay? So, you break up your problem into independent parts which can be processed separately and give that job to 2 different processors, and they work on it in parallel to give you an answer which a single processor would take much more time. So, you can certainly get a lot of advantage by using parallel processing, but here you get much more power because a huge amount of information can be processed simultaneously. It does not mean that if you carry out a measurement, all the detailed information which is sitting over there is accessible to you. It is not, because the moment you carry out an observation, the system collapses into an eigenstate. There is no escape from that, and you are going to get only the result of that measurement. So, you may have 2 to the n states which are being processed, but from if you differ your observation, if you differ the measurement process, then in between you can process a lot of information having these superpositions simultaneously, and you can manipulate that information. Okay. So, in the Deutsch algorithm we already experienced this, that you can manipulate information. So, what the strategy in the Deutsch algorithm, when we used 2 Hadamard gates before you allowed the input to the control F0 gate, was that you enabled it to process all the information at once, all the 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1, all of these possibilities could be processed by that gate in one go, in one step. Okay? So, you cannot get all the intermediate steps information, that is not accessible, but manipulation of a huge amount of information in parallel is achieved using quantum gates. So, Let us consider a 6 qubit quantum computation. Alright, so now there are 6 digits, each can be either 0 or 1, the total number of states will be 2 to the power 6, okay, which is already a large number, right. And suppose your task is the following, that you are given a particular superposition consisting of 4 of these 6 qubit states. Okay? You are given a particular superposition of 4 states, each of them are 6 qubit states with appropriate coefficients, and your task, this is the combination that you are given, okay? And your task is to get a superposition consisting of these 7 states, and you are allowed to use a computer, okay? Because you have to find out in which position you have a 0, in which position you have a 1, okay? And what kind of digital gate you will put it through to check out if you can bring it to this result in which you have got 7 states, all right. And using digital classical computers, you will actually need thousands of steps, okay, because there is a 0 and a 1, only 2 digits, and they will kill you, right. You need thousands of steps, literally thousands of steps. But using strategies, quantum strategies, because you already learned from Deutsch that you can process a lot of information using quantum gates in smaller number of steps. The Deutsch gate enable you to get a result in 1 step for which classical computer will need 2 steps, right. So, the advantage is not just a factor of 2 to 1, you will see now what would require thousands of steps, and not just the function control NOT gate, but you need additional quantum gates which you can work with. You begin with this combination, then put it through a quantum gate, you get this step, 1 step, then you get another through some other quantum gates, and what kind of quantum gates you need is a matter of detail which I am not discussing, okay. But that is something for you to learn about. And then one more and you got the result. Is it not amazing? In just 3 or 4 steps, okay, for what would need thousands of steps. Yeah? And you better learn these techniques because kids are very smart and they would easily throw you out of business in quantum computing very soon, right. So, these are the big advantages of quantum computation. The challenge of course is dealing with the decoherence, because what this assumes is that the coherence is not lost when you put it from one gate to the other to the third and so on, and superposition is very difficult to sustain, because if there is even a minute interaction of the physical system with anything else, so you might do this experiment in vacuum, but what is vacuum? You will be left with something, okay, no matter how good your vacuum pumps are. And if it interacts with it, you know, the system thinks that this is a measurement and let me collapse into my eigenstate, right. So, you lose the coherence. So, it is not easy to do the readout because of this decoherence problem. It is a serious problem, and quantum superposition states are very fragile, which is why it needs the investment of Google and IBM to build these giant machines. These are the sources of problems. So, there is information is lost through interaction with the environment, and the actual physical implementation is very difficult. And some of you perhaps are extremely good experimentalists and you might actually be able to do it. But that requires huge investment, extremely sophisticated laboratories, and huge amount of funding. But notwithstanding that, so far as the coding is concerned, processing information is concerned, which is quantum, all of you certainly need to learn how to code a quantum computer. So, if you Google, you will get easily, if you Google big ideas in computer science, then every course in computer science will mention these: creativity. I think it was always a big idea, but computer scientists would have you believe as if it is their discovery. So, abstraction, this also I think was always a big idea. Data and information, algorithms, programming, internet, and the global impact. So, these are recognized as 7 big ideas in computer science. And then you have algorithms which actually run the world, and our lives are directly impacted by these things. And you have search engine indexing, PageRank technology, the public key cryptography, the public and the private, how these are used, forward error corrections, pattern recognition, data compression. So, these are some of the big things which are used in modern technology, and they impact our lives, all our communication, networking, internet, banking, okay, money markets, everything are done using this. And the cryptography is of great importance in this. And I would like to mention the RSA challenge, the RSA asymmetric cryptography algorithm, which is named after Ron Rivest, Adi Shamir, and Leonard Edelman. Okay, these are the 3 initial letters of their names, RSA. And what is this RSA challenge? So, RSA came up with these big numbers, okay, and asked that prime numbers P and Q exist such that the RSA number can be factorized as a product of P and Q, and how much time do you need to do this factorization, okay. And then you can use your computers, you can use some of the fastest computers which are available to you in the world, right. You can use extremely modern computers which have got parallel processing and huge amount of information that can be stored in the registers. So, all this can be done, and let us look at some of this challenge numbers. So, you have to determine the 2 prime numbers P and Q and find if the product goes to N. So, this challenge was posed in 1991, March 18th, okay. And then these numbers were generated on a computer which had no network connection, so that the information could not have been shared with any other machine in any way. No evidence was left as to how these numbers were generated, and the hard disk was destroyed, so that nobody could have access to the information which was used to generate these numbers. And the challenge was thrown open with a nice prize. For some numbers $1,000, for some other numbers $2,000, and some even more. I will show you some of these things. So this is RSA 100. This is the number. It has got 100 decimal digits, and the challenge is find prime numbers p and q such that n is equal to p times q. Sit down and do it. Okay. And this challenge was met rather quickly after the problem was posed in 1991. This was solved on April 1st, so within 2 weeks. Okay. And Lenstra got $1,000 for this, I think. The factorization took a few days using multiple polynomial quadratic sieve algorithm on a mass parallel computer. Okay. And this is the factorization that you need to break an encryption. Okay. If you want to get into some banking system or break any encryption, okay, the problem will boil down to finding this kind of factorization. And if it is going to take some time, then your key is safe, not otherwise. Okay, if it can be done quickly, but if it is going to take a few days, it is already a reasonably safe encryption. Okay. So these are the factors, and these were determined using this mass parallel computer. Let us have a look at some others. There is RSA 240. This has 240 decimal digits. So these are the factors, and the CPU time spent on finding these factors amounted to approximately 900 core years on a 2.1 gigahertz Intel Xeon 6130 CPU. So these are some of the powerful machines, and this is the equivalent time. Okay, it is not the so many years. Okay, human life is but that is the amount of CPU time it has used. Okay, using those many CPUs, those many parallel processors, all right, and if you add up everything, it amounts to so much. So this is not easy, all right. So this was factored not so long ago, just 2 months ago. So these are very exciting problems of current interest. There is this RSA 768. It has got 232 decimal digits. This was factored in 2009, and it took 2 years to factorize it, and there were brilliant mathematicians who were working their way and programming some of the most powerful machines available. And the CPU time spent on this correspond to almost 2000 years of computing on a single core 2.2 gigahertz AMD machine. Okay. But quantum computers will let you process this information very fast. Okay, and that will obviously impact our lives in a very big way. So, there is this RSA 2048, it has got 617 decimal digits. This has not been factored as yet, but I do not think there is any prize now, because I think RSA has discontinued that, because they established what they needed to, but I am sure somebody is going to factorize it sometime, and the prediction is that it may take some more time before anybody can actually factorize this, but it will be a huge achievement if you can do that. So, now comes the quantum algorithm. This is the Peter-Shor algorithm, and using Peter-Shor algorithm you can do this factorization very rapidly. Okay? So, he devised quantum algorithm for factorization exponentially faster than the best classical computers, and you know what the exponential function means. You take a grain of rice and every single day you ask for 2 to the power the next number on the chessboard, right? And no time you will be the richest man in the world, right? So, the exponential function is amazing, and this is the Shor algorithm. What it takes advantage of is that an n-qubit system can be in 2 to the power n states simultaneously, and it can deal with a lot of information simultaneously. Observation would of course collapse the system into an eigenstate, the superposition would be lost, but in between you can manipulate the superposed states using multi-bit quantum gates. So, that is what quantum computing is about. And there is another very famous algorithm which I would like to mention, that if you have a simple circuit and you have a bulb which is not working, then your suspicion would be that the switch is not working and you need to go and test the switch. But what if there are many switches? Then you do not know which switch is not working, and the on and off positions of the switches may also be upside down in some cases. Okay? Then you need a large number of attempts to figure out which switch is broken. Okay? So, this problem can be solved in much less time. You have 2 to the n configurations for the search. You have to find out, because each switch can be either on or off. So, using the algorithm developed by Lavkumar Grover, who studied at IIT Delhi, your sister institute, and this is a very successful algorithm for search, and you are able to do this in root n queries on a quantum computer using Grover algorithm. So, the Shor algorithm and the Grover algorithm. So, there are 3 famous algorithms, quantum algorithms. There are of course several others, but these 3 are amongst the most famous. The first one is the Deutsch, then you have the Shor algorithm, and then you have the Grover algorithm, and that pretty much is the introduction which I would like to give for this part of the course. And essentially it begins with the question which Einstein raised about entanglement, and the Bohr-Einstein debates led you to some insights into what exactly is entanglement, and then of course the John Bell inequalities gave you the tool to determine whether nature has intrinsic quantum entanglement built into it, and it is not due to local hidden variables. And I mentioned that it is difficult to sustain quantum coherence, but this entanglement, which Einstein described as spooky action at a distance, China was able to maintain entanglement over a distance of 1200 kilometers. Okay? And if this can be done, then of course the coherence is sustainable by using these advances in technology, and then of course using this you can actually make unhackable quantum internet. So that's what tomorrow's technology will be about, or maybe day after tomorrow, but it's coming. Okay, so you can read about the NMR type of computers. There is a lot of information which is available on the internet. If you Google, you will certainly get a lot of information. There are some excellent talks which are available on the YouTube, so please expand your knowledge. I have only attempted to give you a start, and with that I conclude this set of lectures on introduction to quantum computing. If there is any question, I will be happy to take.
When we are talking about the ancillary, why is it supposed to be in a known state? Like, why can't it be in an unknown state? Like,
then it will not be capable of giving you the result that you want. I mean, just think of a photocopying machine. Okay? If you insert a blank paper, then you know that it has the capacity, the potential to give you the copy of what you want to copy. Okay? But if you feed in, instead of that blank paper, a newspaper, yesterday's newspaper, right? Whatever, it is an unknown newspaper. You could always feed in a newspaper which is blank, okay? But then it has to be a known blank state. If it is an unknown sheet that you have inserted, it may be, it will be impossible to produce the copy, especially if that newspaper is a Chinese paper. So it has to be a known blank paper. So the ancillary state has to be a known state. Any other question? It will be bad even if it was an English newspaper. But especially bad if it is Chinese, I think. They're all pictures, right?
so can it be possible that we extract the information from, like we are doing in the experiment where, and use the information and then destroy it, like using then, like it can it be done like that?
Using information involves an intervention.
Okay.
And any intervention destroys the superposition. Any information. Whatever you do is like a marker in the Young's double slit experiment. Its equivalence is simply this, that you have tried to figure out which way the light has passed through. Has it passed through slit 1 or through slit 2? And any attempt to get this information destroys the superposition. And that's the reason Feynman says in his famous lecture that almost everything in quantum mechanics is contained in the analysis of the Young's double slit experiment. So it's always very useful to go back to what your concern would mean in the context of the Young's double slit experiment, and that gives you the immediate answer. that whatever interception you would do is going to destroy the interference, because it's a marker. The system doesn't care whether your motive is to use it or to misuse it or to abuse it, right? The system only reacts to the marking, and if you have marked it, the superposition is lost. Okay, so thank you all very much.